Hello and welcome to our lesson on distributions of data. So we've been talking a lot about different ways to collect data, ways that we could organize it. So we said we could collect through surveys, experiments, observational studies. We said we could organize it using circle graphs, bar graphs or histograms, frequency, polygons or line graphs, and then frequency distributions where you make the two-column table. And then we looked at ways to analyze the data that was collected. So one of the ways was finding our measures of central tendency or finding our measures of dispersion. So we had mean, median, mode, mid-range, we had range, and then we had standard deviation. Okay, so we're going to look at something else here. We're going to look at distributions of data. So when the data is collected, let's say the data is put into a histogram or a bar graph, the general shapes that tend to occur can be described in the bar graph. So the distribution of the data in the bar graph, the way we see it, can be described. So there's some commonly occurring situations that we're going to discuss. One of them more common than any of the others, but let's talk about some of the less common ones first. So when you're examining data using histograms, we can describe the shape of that histogram. We can describe the shape of the pattern that we see in the bar graph using the overall appearance or pattern. Okay, so common types, these are less common than the last one we're going to talk about, but some common types. This first one we call rectangular distribution. Rectangular, or sometimes it's called uniform distribution. These are when your observed values occur with the same frequency. So if you look at the bar graph, we have the first bar that goes up to whatever this value is, but the second bar goes up to the same value, the third one, the fourth one. It's the same frequency for each one of the values. So for example, let's say you were collecting data on rolling a die, because you have no life and you're just going to roll a die a whole bunch of times and see what happens. Well, we would expect long term, because the likelihood of rolling 1, 2, 3, 4, 5, or 6 are all the same, we would expect over the long run that if you were to make a bar graph for the number of 1s, 2s, 3s, and 4s, and 5s, and 6s rolled, that we would have about the same number. Now, it might not be exactly right. Sometimes in your rectangular distribution, you'll see a little bit of variety, like maybe this one's a smidge higher, but if they're all pretty close to the same, we're going to call that rectangular or uniform distribution. Okay? Sometimes you have values that are either constantly increasing or constantly decreasing. And if they're constantly increasing or decreasing, we're going to call that J-shaped distribution. J-shaped, maybe you can kind of see a J. This one's backwards, but maybe you can kind of see a J shape happening in here. And I don't want you to put the blame on me for these names. Okay, I'm just the messenger here, so don't blame me for the awkwardness in the names. So J-shaped distribution, values constantly increasing, constantly decreasing. For example, maybe the number of hours that you're spending studying or completing work for your classes over the semester. So maybe you're starting out real strong, right? At the beginning of the semester, you're spending a couple hours a day, and then as we trickle along here, you're cramming all at the end. So day by day, the hours that you spend are less and less, maybe. Or maybe on the other end, maybe you start out real slow and then you realize, hey, I need to pick this up. So maybe like Monday, you don't do very much. Tuesday, not very much. Wednesday, Thursday, not much. But by Saturday, Sunday, when stuff is due, you're on the computer for like 8, 9 hours, right? So just some examples of J-shaped distribution. Obviously, these types of things occur in real life all the time. The next one, we're looking at two values possibly occurring more than others. So in this graph where there isn't a constant increase or decrease, it's sort of jumping all around. It looks like this value here and this one are occurring or a lot more frequent than the others. And maybe it's going to be a little more clear in some of the pictures, but we're going to call this bimodal. Remember, mode means the most. So bimodal means you have two values that occur more often than any others. So for example, let's say that there were an equal number of men and women in a study and you weighed them all, you'd probably have one average weight for men, you'd probably have another average weight for women, and they're not going to be the same. So you might have a really common sort of area for men and another common area for women, so maybe two. And similarly, like for heights, right? Men are probably generally going to be taller than women are, so you're going to have some common for men, some common for women, but those two are going to be more frequent than anything else. Okay. Here we're going to be looking at distribution that is skewed. Distribution that is, this one is, we're going to call this skewed to the, to the right. And when you have distribution that is skewed to the right, you're going to see some increase and some decrease. So you see this is increasing and then it decreases, but the decrease is more here, and the values are tapering off and tapering off the farther we go to the right. So if it's distribution that is skewed right, you're going to see an increase at first and then a decrease, and it's just going to keep decreasing. It's going to be tapering off to the right. So the values taper off and sort of like zero out here as we go to the right. And then when it's skewed to the left, the other thing happens. So you have a sort of increase this way, but then it tapers off as we go to the left. So let me just get rid of this ugliness I put on my bar graph here. So this is going to be skewed to the left. And when it's skewed left, that means the values taper off as you go to the left. So, I don't know, skewed to the right, maybe you have something like the number of kids per family. So maybe lots of families don't have any kids, and then one kid, and then two is really popular, and maybe less have three, and even less have four, and even less have five, and even less have six, and even less have seven. So you might see an increase at first because 0 is the lowest, right? And then it's going to just taper off. Like 11 kids is really uncommon, right? So the farther you go this way, the less likely you are to have a family that has that many kids. What did I put here for skewed left? I don't know how far students live from school. Sometimes it's hard to think of examples. I guess I could have looked some up, but the distance students live from school, so maybe you have a really popular distance, like maybe most of the kids live within, I don't know, 1 to 2 miles, and then farther away is going to be less kids, and, you know, farther away, or closer to the school, I mean, is going to be even more. So you have distributions that could be skewed left or skewed right, tapering off one direction or the other. So these are common types of distributions, but they aren't the most common. What we see happen the most often is what we call normal distribution. We call it normal because it's the most normal. It's the one that happens the most. So each of the distributions is useful in describing data, but the most common distribution that we see, and the one that is studied the most, is what we call normal distribution. And normal distribution, because it happens the most, it has been studied the most, we know the most about it. Normal distribution, in normal distribution, we have a graph that looks like the one that we're seeing here. The graph for the normal distribution, sometimes it's called the normal curve. Remember, we could make a line graph out of this instead of a bar graph out of this data if we wanted to. So sometimes you'll see a normal curve there instead of the normal bar graph. And sometimes it's called a bell curve because it sort of has this bell shape. Okay, so there's your normal curve, your normal distribution, your normal bar graph. And what happens with this type of distribution is that we are symmetric about the mean. Okay, symmetric about the, what the heck, sorry. Symmetric about the mean. So what happens with normal distribution is that your mean, median, mode all happen at the exact center. So the mean, median, mode are all at the exact center of the distribution, and then it's symmetric. So you can see if we were to fold that graph in half that the two halves are sort of matching up. So you have a symmetric increase on one side and decrease on the other side. So the increase here and the decrease here are going to be the same. Okay, so that symmetry is the sameness on both sides. And because we're symmetric about the mean and we have that symmetry on both sides, there is exactly 50% over here and 50% over 50% of the data on the left and 50% of the data on the right. So 50% of data falls or is greater than or is right of the mean. and then 50% of the data is less than or to the left of the mean. Okay, so you have symmetry exactly. You have the mean, median, mode all exactly in the middle, half the stuff above, half the stuff below, and increasing and decreasing above and below at the same rate. Okay, so that is the gist of normal distribution, but there's even more to it than that. So with normal distribution, we have something we can apply called the empirical rule. The empirical rule says not only do we know that the mean, median, and mode are exactly in the middle, and not only do we know that there's exactly 50% above the mean and 50% below the mean, but we know the exact percentages that lie within certain standard deviations of the mean. Okay, remember the Michelin tire problem we talked about, where we had the Michelin tires lasted on average 35,000 miles, and then this was the average, which we could say is the mean. Okay, and then we said the standard deviation was 10,000 miles. And so we added and subtracted 10,000 miles. We said most of the tires would be, if we subtracted 35,000 would be 25. If we added it would be 45. We said most of the tires were going to be lasting between 25 and 45,000. Okay, this is the sort of concept we're going to be looking at here. When I say most of them were going to last between 25 and 45,000, it's a little more specific than that. Here, what we know with this empirical rule that is attached to normal distribution is that 68% lies within one standard deviation of the mean. So let me go back here. Within one standard deviation means if we subtracted the standard deviation once, that's what we did here, and we added the standard deviation once, that's what we did here, that 68% of the data would be within that range. So 68% of the Michelin tires lasted there. Now let me just put this on the normal curve for you, okay? This normal curve for this Michelin tire problem, we said 35,000 was exactly the middle. And then if we added 10,000, the standard deviation of 10,000, if we added it once, we'd get to 45,000. If we subtracted it once, we'd get to 25,000. What this empirical rule says is that there's 68% of tires that are going to be lasting in that window of mileage. Okay? Now, we also know that 95% of the data lies within 2 standard deviations. 95% lies within 2 standard deviations. So that means if I added the standard deviation twice or subtracted the standard deviation twice. So if I added another 10,000 here, I'd be at 55,000. And if I subtracted another 10,000 here, I'd be at 15,000. So what the empirical rule says is that 95% is going to be in that range. 95% of the tires would be lasting between 15 and 55,000 if this was normal distribution, okay? And then one step further, 99.7% of the data in normal distribution will be within 3 standard deviations of the mean. 99.7, that's just about all of it, okay? So almost all of the data, if we went are within 3 standard deviations of the mean. So I added the standard deviation once, twice. If I added a third time, I'd be at 65,000. And then I subtracted once, I subtracted twice, and if I subtract a third time, I'm down to 5,000 here. Okay, what the empirical rule says is that 99.7, okay, this was 68, 95, and then 99.7, almost all of the tires. Okay, there's going to be a couple of random exceptions, but 99.7% of them are going to last between 5 and 65,000 miles if this is normal distribution. Okay, so back here, again, normal distribution. So we have 68% within 1 standard deviation. And notice on the bottom here, these little labels on your axis here, that's for the number of times you would add your standard deviation or subtract it. So adding, that's why these are positive. If you added once, added twice, added 3 times, subtracted once, subtracted twice, subtracted 3 times. So if you're adding 1 time, there's going to be 68% that's in that window. Okay? And then, sorry, let me just, 68% that's within 1. And then if you added and subtracted twice, you're going to have 95% that's within 2 standard deviations. And then if you added and subtracted 3 times, then 99.7 is going to be within those 3 standard deviations. Now, we also have symmetry, right? So think about this 68%. Okay, the 68% that's in here, because there's symmetry, if we cut that in half, that means there's 34% that goes in here, and there's 34% that goes in there. Okay? Now, again, symmetry, if we looked at this 95% window, if I took out the 68% and cut what was left over and took out, so, sorry, we have 95% in this pink range, okay? If we subtract out the 68% that we know is in that within the 1 standard deviation, subtract out the 68%. Let me use my calculator here. If I have 95 in that window altogether and I subtract out that 68%, that leaves me 27%. If I cut that in half, because there's symmetry here, the little piece that's left here and the little piece that's left here, if I divide 27 by 2, I said divide, there we go, by 2. That leaves 13.5% to go in this little section and 13.5% to go in that section. Okay? And then we said 99.7% would go here. Now if I took out the 95% that was covered, if I took that out, what would left and divide by 2, what's left? There's going to be 2.35 in this little area and 2.35% in this little area. Okay? So these little markers are for in these columns. So this column has 2.35%, or this column has 13.5%, and so on. And then this was 99.7, right? 99.7% of the data is going to be within those 3 standard deviations. If we take that away from the 100% total, right? There's 100% of data total. If we take out the 99.7 that's captured within the 3 standard deviations, there's 0.3 left because there's symmetry. If we cut that in half, then there's going to be one little 0.5 left and 0.5 left out here and out here beyond those markers. Okay? Alright. Hopefully I'm not muddling this up for you too much. So let's try to look at a couple situations where we apply this empirical rule. Let's suppose that the weights of newborn babies are normally distributed, and 2,000 babies are born at Banner Thunderbird each year. Okay, so if they're normally distributed, that means you have this sort of bell curve happening here. So normal distribution, that means there's going to be 68% within 1 standard deviation, 95% within 2, and then 99.7% within 3. Okay? So it says how many, if 2,000 babies are born at Banner Thunderbird Hospital each year, how many are expected to weigh within 1 standard deviation? Well, within 1 standard deviation, we said that's 68%. And there are 2,000 babies, so 68% of 2,000. Calculator will do this for you. 68%, 68, and remember if you go to your keyboard and hit the percent, it'll do the 68% of, and we wanted 2,000, and that's 1,360. 1,360 babies. So if there are 2,000 babies born, we would expect 1,360 of them to weigh or to be within 1 standard deviation. So like, let's say the average was 10 pounds, and there was a standard deviation, the mean was 10 pounds, and there was a standard deviation of 1. So if I added 1, I'd get to 11. If I subtracted 1, I'd get to 9. Then we would have 68% being between 9 and 11 pounds. Okay, that was just a what if. And then this math if you were not using Desmos and it didn't have that percent button. 68% of 2000, 68% is 0.68. Of means multiply. If you multiplied 0.68 times 2000 times 2000, come on, you're going to get the same thing. So that's the math behind that, okay? Now, within 2 standard deviations, so 68% would be within 1. According to the empirical rule, 95% would be within 2 standard deviations. So it's 95% of 2000. Let's change this to a 95, and that would be 1,900 babies. Okay, so there's that. Now let me just show you another one where we can put some more of the numbers in practice. Let's suppose that the mean weight for the babies was 8 pounds and there was a standard deviation of 1 pound. So if the babies at this Banner Thunderbird Hospital, if the mean weight is 8, in your distribution, the mean of 8 then, because it's normal distribution, would have to be right there in the center. Okay, so half the babies weigh less than 8 pounds, half the babies weigh more than 8 pounds. So that 8 pounds, the mean of 8 pounds goes in the middle. Sorry, the mean of 8 goes in the middle. And then if the standard deviation is 1 pound, if the standard deviation is 1 pound, that means we add and subtract 1 pound. If I added it once, I'd take it to 9. If I subtracted it once, I'd be to 7. So that's within 1. That's 1 standard deviation above. That's 1 standard deviation below. And this is right at the mean, right? If I added and subtracted it twice, so if I added the standard deviation a second time, I'd get to 10. If I added it a third time, I'd get to 11. If I subtracted it a second time and subtracted it a third time, then I'd be to 6 and then 5. So we're going up and down by 1. So this is telling me to add and subtract 1. Okay? Now, according to the empirical rule, we said there would be 68% within that 1 standard deviation. So technically there was going to be 34% here and 34% here. And then if there was 95% here minus the 68 divided by 2, that there would have to be 13.5% here and 13.5% here. And then 99.7 here minus the 95 divided by 2 told us they would be 2.35% in this little area and 2.35% here. And then the 100% minus that 99.7 cut in half said there would be 0.15% here and 0.15% here. So outside of the 3 standard deviations. So that's our empirical rule. And this time with our mean in the middle and our standard deviation of 1, so adding and subtracting 1, we know exactly where everybody is in this distribution. So if I asked you a question like, what percentage of babies weigh at least 8 pounds? At least 8 pounds means 8 pounds or more. 8 pounds or more would be this much of the graph. 8 pounds or more. How much of the graph is that? Well, that's 50% of it. So 50%. Oops, 50%. Okay. What about between 8 and 9 pounds? Between 8 and 9 pounds, that's this little area here. Well, we said that's half of the 68, so that would be 34%. Or less than 10 pounds. Less than 10. So here's 10. Less than 10 would be all of this. Okay, so 2 ways we can get that. We can add up all the numbers we've highlighted there, or we could subtract these 2 from 100. Either way, we're going to figure out what that is. So I'm going to take 100%, and I'm going to subtract out the 2.35 and the 0.15, and that gives me what? So I had 100% of the graph, and I wanted to get rid of the 2.35. Gosh, 3. I'm having issues here, people. 3.5 and 0.15 at the end. Okay, so that leaves me 97.5 left. 97.5%. Okay, how about more than 9 pounds? So 9 pounds is here. More than 9 pounds would be this area. So we'd have to add 13.5, 2.35, and 0.15. So we would add 13.5 and 2.35 and 0.15. And that's going to be 16%. And then between 6 and 8 pounds, between 6 and 8 pounds would be here. So we'd be adding 13.5 and 34. So 13.5 plus 34 is going to be 47.5%. All right, so that's how we can use our empirical rule for normal distribution. Kind of helpful to know what percentage of babies are weighing within these standard deviations. So again, just wrap your head around this, okay? If the mean weight for babies was 8 pounds, that means half the babies are less, half the babies are more. Or that 68% of the babies weigh within one standard deviation, weigh between 7 and 9 pounds, and etc. Okay? Let's look at one more. Suppose the math scores on the SAT are normally distributed with a mean of 500 and a standard deviation of 100. We want to draw the bell curve and use it to determine the percentage of students that score at least a 700. So a mean of 500, that's going to go in the middle. Mean of 500 goes in the middle. So we're going to start with 500 there. That means on this SAT test, that's your mean, that's your average, that's your middle. But half of the students, this is just the math portion, half the students score below that and half of the students score above that. And now it says that the standard deviation is 100. So we're going to add and subtract 100 to move along this bell curve. So adding 100 as we go this way, 600, 700, 800. Subtracting 100 as we move the other direction, so 400, 300, 200. Okay, so this was adding the standard deviation once, adding it twice, adding it 3 times. This was the mean, so we didn't add or subtract the standard deviation. This is subtract it once, subtract it twice, subtract it 3 times. And according to the empirical rule, 68% are going to be scoring between a 4 and 600, 95% scoring between a 3 and 700, and 99.7, just about everybody scores between a 2 and 800. Okay, now this question says to use the empirical rule to determine the percentage of students that score at least a 700. So at least a 700 would be a 700 or more. So what percentage of students are in that area? Well, this would be the 2.35%, and this one was the little 0.15%. So if we add those, we're looking at 2.5%. So we're going to say 2.5% score at least a 700. That's not a lot, okay? Not a lot of people in that range because that math part of the SAT is challenging, okay? Hopefully this is making a little sense. You have some practice to work on, so give it a try. And as always, if you need some help, just reach out. I'm here for you guys. All right, take care.